Hello, my name is George Hess and I will present Masked Autoencoder for Self-Supervised Pre-Training on Lidar point clouds. This is joint work done together with Johan, Elias, David, Christopher and Lennart. In this work, we propose to use Masked Autoencoder pre-training for automotive point clouds. In the automotive domain, raw data for self-supervised learning is cheap, while annotations are expensive and time-consuming to create, making it a suitable candidate for pre-training. While MAE originally was used for images, this type of pre-training has also been explored for point clouds. Similar to image patches of equal size, Point MAE divides the point cloud into clusters of equally many points. Overlapping clusters create redundancy and are not suited for sparse automotive point clouds with varying point density. Therefore, we propose Voxel MAE, a pre-training tailored to the widely used voxel representation. We use a unique set of reconstruction tasks to capture the characteristics of Lidar point clouds. Our experiments show that Voxel MAE can reduce labeling efforts by 40%. Before diving into Voxel MAE, let's give some background on the original MAE approach. Masked autoencoding is a simple yet effective feature learning paradigm for pre-training encoder backbones. Given an image, divided into equally sized non-overlapping patches, then randomly mask a large portion of these patches. Next, the visible patches are fed through an encoder. Here, a transformer is used as it elegantly handles varying sequence lengths. The encoded patches are concatenated with the masked patches and fed through a decoder. Masked patches are represented as a learnable mask token and some positional embedding. Finally, the decoder aims to reconstruct the original image. After pre-training, the encoder can be used on unmasked images and fine-tuned for different tasks. MAE's effectiveness has been shown for classification, object detection, and so on. Multiple approaches have applied the MAE method to point clouds. By combining furthest point sampling and k-nearest neighbor, the point clouds are divided into clusters of equally many points. The reconstruction consists of predicting point locations within each cluster. The other aspects of MAE remain the same. While effective for dense point clouds with a single object or for indoor data, this point cloud representation does not scale for automotive data. Therefore, these encoders cannot be used for downstream tasks like 3D object detection in Lidar point clouds. Our method, Voxel MAE, is instead tailored toward the voxel representation, which is popular in the automotive domain for tasks like detection, segmentation, and tracking. Similar to patches and images, the point cloud is divided into equally sized and non-overlapping voxels. However, different from images, the majority of voxels are empty and do not contain any points. These voxels are discarded for computational efficiency. Next, among the non-empty voxels, we mask out 70% and replace these voxels with a learnable mask token. The remaining voxels are embedded with a voxel feature encoder. The voxels which have not been masked are encoded with SST, which is a transformer backbone using the shifting windows idea from Swin, but in 3D. This can be compared to the use of vanilla transformers in previous work. For the decoding and reconstruction, we again add the previously masked voxels. However, only feeding voxels which contain points to the decoder would greatly simplify the reconstruction task. For instance, the absence of voxels could give information about object contour. Therefore, we also feed mask tokens for randomly sampled empty voxels. These use the same mask token as non-empty voxels, forcing the decoder to learn how to discriminate between empty and non-empty voxels. Finally, we apply a prediction head to reconstruct the masked voxels. For simplicity, the head predicts a fixed number of points per voxel, which is supervised with the chamfer distance to the true points. To still learn the unique characteristics of point clouds, we also predict the number of points in each voxel, and also apply a binary classification task whether each voxel is empty or not. After pre-training, we use the encoder to initialize the backbone of a 3D object detector. We compare its performance to a randomly initialized model on the new scenes dataset. We pre-train the model on the entire training set, but vary the amount of labels available during the fine-tuning. Voxel MAE brings large gains when only 20% of the data is available. Moreover, these trends hold also when the amount of labels is increased, proving the effectiveness of our approach. Further, we can see that Voxel MAE only requires 40% of the annotations to outperform its randomly initialized equivalent. We also compare Voxel MAE to other self-supervised approaches for object detection and find it to be competitive in terms of performance boosts. Note, however, that these methods have been applied to different backbones. We should also acknowledge that transformer backbones in general still lag behind CNNs for Lidar 3D object detection, but we hope that this is one step to start closing this gap. To summarize, we propose a method for applying MAE pre-training to voxelized point clouds. We show that Voxel MAE greatly reduces the need for manual annotation and that it boosts the overall performance when using all available labels. Thank you for listening.